Welcome to the Deep Dive. We're the show that takes complex ideas, digs through the sources, and brings you the key insights. Today we're diving into something called causal inference. Basically, how can we really know if one thing causes another, especially when we can't just run a perfect experiment? And to kick things off, let's talk chocolate. Seriously, have you ever heard this correlation? Countries that eat more chocolate per person also tend to have more Nobel laureates per person. It's kind of wild, right? Think about Switzerland, huge on Nobels, huge on chocolate. So, the million-dollar question is this actually causal? Could, governments boost Nobel Prizes by handing out more Toblerone?
Probably not. Your intuition is likely screaming no there.
Yeah, seems a bit too good to be true.
And it probably is. There's a much more plausible explanation, isn't there? Wealth.
Ah, right. Wealthy countries. They invest more in science, which leads to Nobels.
Exactly. And populations in wealthy countries also tend to buy more luxury goods like, well, nice chocolate.
So wealth could be this hidden factor, this common cause.
Precisely. It's what researchers call an omitted variable. And failing to account for it leads to omitted variable bias. It makes it look like chocolate causes Nobels, when really, wealth might be driving both.
Got it. So our mission today is to figure out how we move past just seeing these correlations, these associations, to finding actual cause and effect. Even when the thing we're studying, maybe it's chocolate eating, maybe it's a job program, isn't assigned randomly like in a lab.
We're essentially looking for the tools that let us make fair apples-to-apples comparisons using real-world observational data, helping you cut through that statistical noise.
Okay, let's unpack this then. We see correlations everywhere, like the chocolate one, and it's so tempting to jump to cause and effect. But as we just said, often there's something else going on. So the big challenge is, how do we pin down the average causal effect of some treatment? Could be anything using stats, especially when people weren't randomly chosen to get it, when it depends on other things.
Like country wealth in our example. Those other things are what we call covariates.
Right, covariates. And the approach involves, what's it called, the adjustment method?
Yes, the conditional or adjustment method. The core idea is simple, really. You compare units, people, countries, whatever, that look the same, that are comparable on those key covariates.
Okay, comparable units, but what makes this work? There must be a catch.
There is, and it's a big one. The key condition, the linchpin, is something called conditional ignorability. You might also hear it called conditional exogeneity or unconfoundedness. Fancy names. But the idea is...
Let me guess. If you control for the right things.
Exactly. If you can account for or condition on the right set of observed characteristics, those covariates X, then the treatment you're studying, D, looks as good as randomly assigned within groups that share the same X. It's like you found little natural experiments hidden in your data.
Okay, that sounds powerful. But what happens if you don't account for the right things? That's confounding, right? Like with the chocolate.
Precisely. Let's take another example from the sources to really nail this confounding idea. Think about, say, smoking marijuana and life expectancy. Okay.
Now let's imagine, just hypothetically, that marijuana itself has zero actual causal effect on how long you live. The true delta is zero.
Right.
But in the real world, the decision to smoke marijuana might be linked to other choices, other behaviors. Let's call these X, maybe things like drinking alcohol heavily. And those behaviors do shorten lifespan.
I see where this is going.
So if you just look at the raw data without thinking about alcohol use, you might see that marijuana smokers live shorter lives. But it's not the marijuana causing it in our hypothetical. It's the associated behavior, the alcohol, that's doing the work.
So the simple regression is misleading.
Totally misleading. That gap between what you observe predictively and the true causal effect, that's confounding, or sometimes called selection bias. People weren't randomly assigned marijuana. Their choices were related to other factors influencing longevity.
But you're saying we can potentially fix this?
Yes, that's the crucial part. If we properly condition on X, in this case, maybe measure and control for alcohol consumption and other relevant lifestyle factors, we can remove that confounding bias. Assuming what?
Assuming that once you've accounted for X, any remaining differences in who smokes marijuana are essentially random with respect to their potential longevity. The potential outcome, how long they would live, is independent of their marijuana use given their other behaviors X.
Wow. Okay, so this relies really heavily on some big assumptions then. It feels like you need to know exactly what to control for.
You absolutely do. And that brings us to the formal assumptions. The first big one combines two ideas, conditional ignorability and consistency.
Okay.
Conditional ignorability is what we've been talking about. For any potential outcome, like your lifespan if you did smoke, Y1 versus if you didn't Y1, your actual treatment status, D, is independent of those potential outcomes once we condition on the covariates X.
And consistency.
Consistency is simpler. It just means the outcome we actually see for someone, Y, is a potential outcome corresponding to the treatment they actually received, YD. If you took the pill, your observed health is your health if you took the pill. Seems obvious, but it's technically an assumption.
Okay, so if those hold, what's the implication?
The implication is huge. It means if you can group together units, people, firms, whatever, that have the exact same values for those covariates X, then within that group, who got the treatment and who didn't is basically random. It's like you've created a mini RCT within your observational data.
That's pretty cool. You mentioned something else, though, a propensity score.
Ah, yes. The propensity score. This is a really clever idea, often written as PX. It's simply the probability of receiving the treatment, D1, given a specific set of covariates XX, PD1X.
So instead of juggling, say, age, income, education, location, you calculate one number that summarizes the chance someone with those characteristics got the treatment.
Exactly. It's a sort of summary score of how likely someone was to be treated based on their observable characteristics. We'll see why that's so useful in a minute.
And there was one more assumption.
Yes, overlap, sometimes called full support. This is more practical. It just means that for any possible combination of covariates X you observe in your data, there has to be some chance of being treated, D1, and some chance of not being treated, D0. The propensity score, PX, has to be strictly between 0 and 1.
Why is that important?
Well, think about it. If everyone with characteristic X always got the treatment, so PX1, then you have no untreated people with that characteristic to compare them to. You can't estimate the treatment effect for that group because you lack a control group with the same X. Overlap ensures you actually have comparable treated and untreated units for all the different X values in your population.
Okay, makes sense. So conditional ignorability, consistency, propensity score, overlap. If we can reasonably believe these assumptions hold, what's the big prize? What do we gain?
The prize is, well, potentially finding the true causal effect. This brings us to a really key result, Theorem 5.2.1, which basically says conditioning on X removes selection bias. Under conditional ignorability and overlap, that observed relationship we see in the data, the average outcome Y, given the treatment D and the covariates X, written EYD, X, that actually equals the average potential outcome Y given X, written EYDX.
Whoa, okay, translate that a bit.
It means the difference you see between treated and untreated groups with the same X in your data reflects the true causal effect for people with that X. The conditional average predictive effect, which you predict from data, equals the conditional average treatment effect, the real causal effect for that group.
Wait, overall?
And crucially, the overall average predictive effect, APE, equals the overall average treatment effect, ATE. If you average correctly across all the X's, the bias washes out. It's a massive result for observational studies.
So we can potentially get the same answer as a giant, maybe impossible randomized trial.
Under these assumptions, yes. That's the goal. And people often use visual tools, causal diagrams, directed acyclic graphs, or DIGs, to map out these relationships. They show how X might affect both the treatment D and the potential outcomes YD, creating those non-causal backdoor paths. Conditioning on X essentially blocks those paths, isolating the direct causal effect of D on Y.
This sounds like we're heading towards using regression, something familiar?
We are indeed. Many of these ideas connect directly to regression analysis.
Right, how?
Well, in the simplest case, imagine the relationship is truly linear. So the expected outcome Y is just alpha times the treatment D plus some linear function of other covariates, let's call them W, which are based on X. So EYD, W is alpha D plus beta W.
Okay, a standard linear regression model.
Right. If that model is correctly specified and our conditional ignorability assumption holds based on W, then that coefficient alpha directly estimates the average treatment effect, delta. This assumes the effect is the same for everyone, what we call homogeneous treatment effects.
But effects are often different for different people, right?
Absolutely. So we can use a more flexible model. We can include interaction terms like EYD, X, at least alpha 1D, plus alpha 2WD, plus beta 1, plus beta 2W. Here, the effect of D depends on W.
So the effect changes with characteristics W.
Exactly. In this setup, alpha 1 represents the baseline ATE, and the conditional average treatment effect, CD, for some of the characteristics ATE, would be alpha 1 plus alpha 2W. It allows for heterogeneity.
And how do we estimate these alphas and betas?
You can use standard methods like ordinary least squares, OLS, or more advanced techniques, sometimes called partialing out methods like Frisch-Wall level, or even things like double lasso regression, especially if you have a lot of covariates W.
But there's a big if here, isn't there? What if that linear model or even the interaction model is just wrong? What if it doesn't capture the true relationship?
That's a huge risk. It's called model misspecification. If the model you choose doesn't accurately approximate the true conditional expectation function, EYDX, then the coefficients you estimate, like alpha, might not have a valid causal interpretation at all. You could get biased results.
So relying only on, say, simple linear regression could be dangerous.
It definitely can be. And this limitation is a major motivation for using more modern, flexible machine learning methods in causal inference, which we might touch on later. They aim to approximate these EYDX functions without imposing such strong assumptions like linearity.
Okay, so that's one route. Model the outcome Y directly, conditioning on D and X, trying hard not to misspecify. But you hinted there might be another way. What if modeling that outcome process is just really, really hard?
Exactly. Sometimes you might feel more confident about modeling why people got the treatment in the first place, rather than modeling the outcome itself.
You mean focusing on the treatment assignment, the D?
Yes. What if we have a better handle on the treatment selection process? This brings us back to the propensity score, PX, that probability of getting treatment given X.
Okay. How does focusing on PX help?
This leads to an alternative approach, often associated with the Horvitz-Thompson method, which uses propensity score reweighting.
Reweighting, like giving some people more importance than the average.
Precisely. Imagine a simple case, a stratified RCT. Maybe you randomly assign treatment, but you deliberately assign it with different probabilities to different groups based on their characteristics X. Say 60% chance for young people, 40% for older people.
Okay, so the probability isn't 50-50 for everyone, but it is known because you designed the experiment.
Right. In that case, the probability of getting treatment, P of X, is known by design. The Horvitz-Thompson idea says you can estimate the average outcome for, say, the treated potential outcome Y1 by taking the people who actually got the treatment, D1, observing their outcome Y, and then weighting each person's outcome by the inverse of their probability of getting treated, 1px.
Whoa, so you divide their outcome by the chance they had of getting the treatment. People less likely to get treatment get weighted up more.
Exactly. And similarly, you estimate the average Y0 using the untreated people, weighting them by 1px. It essentially creates pseudo-populations where everyone effectively had an equal chance of being treated, balancing the groups.
So this Horvitz-Thompson theorem, it says this reweighting trick works to get the true average potential outcomes.
Under the right assumptions, yes. There's something called the Horvitz-Thompson transform, often denoted H. For treated units, D1, H is 1px. For untreated units, D0, H is next to 1, E brag x. The theorem shows that the overall average treatment effect, ATE, is simply the expected value of the outcome Y multiplied by this transform H. So AE equals EYH.
That seems almost too simple. Just reweight and take an average.
It's elegant, but there's a caveat. While it works for identifying the AE, using only propensity score reweighting isn't always the most statistically efficient way.
Meaning the estimate might be noisy.
Right, might have a large variance, doesn't necessarily use all the information available on how the covariates X relate to the outcome Y. More advanced methods like augmented inverse propensity weighting or double machine learning combine both the regression idea, modeling EYDX, and this reweighting idea to get estimates that are often more precise and robust.
That makes sense. Use both parts. Now, this whole approach relies heavily on getting that propensity score PX right, doesn't it? Especially in observational studies where it's not known by design.
Absolutely critical. If your model for PX is wrong, the reweighting won't properly balance the groups, and you'll still have bias.
So how do you check if your PX model is any good?
That's where covariate balance checks come in. They are super important. Remember, the whole point of conditioning or reweighting is to make the treated and untreated groups look similar, comparable, in terms of their observed covariates X.
Right, apples to apples.
So after you estimate your propensity score and calculate your weights, you should check. Do the average values of the covariates X still differ significantly between the reweighted treated and untreated groups?
So you check if the reweighting actually worked to balance things out?
Exactly. If conditional ignorability holds and your PX model is correct, then after reweighting, the covariates X should be balanced. They shouldn't predict treatment status anymore within the reweighted sample. If you find significant imbalance after reweighting, it's a red flag. It suggests either your conditional ignorability assumption might be wrong or your propensity score model needs improvement.
That seems like a crucial diagnostic step.
It absolutely is. You should always perform balance checks. And interestingly, you can also think about the KD, conditional average treatment effect, in this context. It can be estimated by predicting that transformed outcome, YH, using the covariates X, maybe with regression.
Okay, this is fascinating. We have the direct regression approach, and now this reweighting approach using the propensity score. But this leads to something you mentioned earlier, which sounds really cool. This idea from Rosenbaum and Rubin back in '83, that maybe you don't need all the individual covariates X to adjust for bias.
Ah, yes. That is a truly remarkable finding. They show that if conditional ignorability holds with respect to a set of covariates X, then it also holds if you just condition on the propensity score PX alone.
Wait, just the single PX number is enough? Instead of maybe dozens of X variables?
Correct. The propensity score PX acts as a balancing score. It's a minimal sufficient statistic for removing bias under ignorability. It contains all the information from X that's needed for balancing the groups.
That seems incredibly powerful. Why?
Think about it practically. If you have a situation, maybe an experiment or a very well-understood selection process, where you know the true propensity score, PX, you don't need to control for all the individual X's that went into calculating it. You could just control for PX itself, perhaps by stratifying on it, matching on it, or including it as a single regressor in your outcome model.
So it simplifies things massively, especially if X is high-dimensional.
Hugely. Now, you might still want to include transformations of PX, like polynomials, in your model for flexibility. And sometimes, including other functions of the original covariates X, let's call them W, in addition to PX, can still improve the precision, reduce the variance, of your estimate, even if they aren't strictly needed for bias removal once PX is controlled for, especially if some W's failed those balance checks earlier.
But there's still that fundamental limit, right? This only works for observed confounders, the X's we measured.
Absolutely. This is the Achilles heel of all observational studies relying on ignorability. If there are important unobserved factors that affect both treatment selection and the outcome, and they aren't captured by our measured X's, and therefore aren't in PX, then controlling for X or PX won't remove the bias from those unobservables. There's no magic bullet for unmeasured confounding using these methods alone.
Still, it's a very useful concept. Did you mention something about a clever covariate?
Yes, that ties back to the Horvitz-Thompson transform H. We discussed H equals dpx, 1bpx. It turns out that a very simple way to estimate the average treatment effect, ATE, is to just run a simple OLS regression of the outcome Y on this single constructed clever covariate H.
Just Y regressed on H?
Essentially, yes. Potentially with an intercept. The coefficient on H in that regression gives you an estimate of the ADE. It's a neat shortcut.
Does it give you the CANI too? The varying effects?
No, this specific simple regression trick is just for the overall ADE. It doesn't directly reveal how the effect might differ across individuals with different characteristics.
Okay. Now, most of this discussion has been about the average effect across everyone, or maybe conditional on X. But often we care about specific groups, don't we?
We certainly do. Policy questions are often group-specific. Does a training program work better for younger workers than older workers? Does a drug have different effects for men versus women?
So how do we handle that?
This brings us to group average treatment effects, or GATEs. Let's say G is an indicator for belonging to a specific group. G1 if you're in the group, G0 otherwise. The GATE is the average treatment effect specifically for that group, EY1, Y0, G1.
So the effect for, say, the younger people only.
Exactly. And you can identify these GATEs using the same tools. You can estimate your conditional average treatment effects, CATEs, using regression or other methods, and then just average those CATEs over the individuals within the group G1. Or you can apply the propensity score reweighting methods, but calculate the final average only using the individuals in group G.
That seems straightforward enough. Adjust for confounding, then zoom in on the group average.
Pretty much. It allows for much more nuanced analysis than just looking at one overall average number.
Now, related to that, what about the effect specifically on the people who actually chose or received the treatment? Is that different?
Yes, and it's a really important distinction, especially for evaluating programs or policies. This is the average treatment effect on the treated, or AT.
ATK. What's the formal definition?
It's EY1, Y0, D1. It asks, for those people who actually got the treatment, D1, how did their outcome why one compared to what their outcome would have been had they counterfactually not gotten the treatment.
Okay, so it's a very specific counterfactual question about the treated group.
Exactly. Think about a job training program again. The ATE asks about the average effect if everyone hypothetically took the program versus if no one did. The AT asks for the people who actually went through the training, how much did their earnings improve compared to what they would have earned without the training?
That sounds incredibly relevant for seeing if a program was worthwhile for the people it actually served.
It's often the key parameter for policy evaluation. Did the program benefit its participants? Now, identifying the AT sometimes requires slightly weaker assumptions than identifying the AT.
Oh, how so?
Well, for the AT, you mainly need to be able to figure out the missing piece, EY0D1. That is, what would the treated group's outcome have been if they hadn't been treated? You already observe EY1D1 directly from the data. It's just the average outcome of the treated. So the ignorability assumption might only need to hold for the Y0 potential outcome, or the overlap assumption might only be needed for the treated group having some chance of not being treated.
So it's sometimes easier to estimate than the full AT.
Potentially, yes. And the methods we discussed, like regression adjustment or propensity score methods, can often be adapted to estimate the AT. For instance, the Horvitz-Thompson reweighting can be modified to target the AT specifically.
Wow. Okay, we've covered a lot of ground here. We started with that slightly silly chocolate and no bells example.
A good starting point, though.
Yeah, it really highlighted the issue of correlation versus causation. And we've journeyed through confounding the crucial idea of conditional ignorability.
The bedrock assumption, really.
Yeah. That lets us make these apples-to-apples comparisons by controlling for observed factors, these covariates X, either by directly adjusting for them in a model,
Or through that elegant backdoor route, using propensity scores, PX, to reweight or balance the groups.
It's all about trying to strip away those misleading correlations caused by hidden factors.
Absolutely. What's really powerful, I think, is that these concepts give us a structured, systematic way to ask and potentially answer those what-if questions using real-world data, even when a perfect experiment is off the table.
It helps you cut through the noise, spot the potential biases,
And hopefully arrive at insights that are much more reliable, more actionable than just looking at simple correlations.
And so that wraps up our deep dive into causal inference using conditional ignorability. It's clear that figuring out true cause and effect is challenging, right? Especially because we can't always measure everything. That shadow of unobserved confounding always looms.
It does. Humility is key.
But armed with these tools, thinking about ignorability, propensity scores, balance checks, 8E, 8T, you're definitely better equipped now to critically evaluate claims about cause and effect that you encounter everywhere.
To ask the right questions about the data.
So thinking about all this, what's the one thing that really stands out to weigh you from our discussion today? And maybe more importantly, what new questions does this spark for you about cause and effect in the world around you beyond the examples we used? Something to chew on.